All right. Well, it is 10 a.m. Welcome, everyone, to the 10th installment of our Long Coffee Break. My name is Andrew Tobin, sales engineer here at Long. Um, so, everybody here at Long is very excited about our newfound relationship with Multistack. Couldn't be more excited to have Pat Karras with us this morning. And what we're going to be discussing is heat recovery chillers. So, Pat, go ahead and take it away.
Great. Well, good morning, everyone. I think it's still morning. I'm actually an East Coaster, so it's just noon to me. But glad to be able to do this with you, and we're really thrilled about our partnership with Long. We have put Long as our representation in Colorado, Utah, Montana, and Wyoming. All of that has been underway now for about anywhere from 2 weeks to a month. But quick history on Multistack. For those of you who don't know, we're into our 30th year now. We've been around since 1989. It was started by three gentlemen who kind of got let out of the acquisition between American Standard and Trane. At that time, they were in La Crosse, Wisconsin. They said, we're chiller guys. Let's start a company that doesn't directly compete, but fills in the gaps that the bigger guys were doing. So that's where the modular product line came from. But for those of you who know us, there's much more to Multistack now. We've gotten into much bigger equipment. We use the Danfoss Turbo Core as well for flooded machines. But what's really grabbed our attention in the last few years is this concept of heat recovery. It's not a new concept. We didn't invent it, but we think we've done a really nice job of I won't say perfecting it because you're always learning, but about 30 to 40% of what we do has a heat recovery component in it. So we're going to spend this morning talking about some heat recovery opportunities. And then if you want to know more, please get with your Long representatives and they will be able to expand on all of the opportunities that exist here. So what's wrong with this picture? This is really what drives the heat recovery process. Almost every building has a heat creation system, a boiler, and a heat disposal system, a chiller of some sort. And the problem with that is oftentimes they might be oversized. And what ultimately occurs as a result of that is you end up actually throwing some of that heat, which you already own, already have created, out into the atmosphere. And so why do that? Let's grab some of that, let's bring that back in and use it if we can. And that's the concept that Multistack has been advocating now for many years. Where does it apply? It would apply in any 4-pipe building where chillers might start at 3 tons. We've done them all the way up to about 700 tons. What kinds of buildings? Hospitals, educational facilities, colleges, universities, primary and secondary types of applications, hotels and process type applications as well. All of those types of facilities would be potential locations for a heat recovery type of application. It's gotten so much attention that ASHRAE 90.1 is looking to get 7% of heat recovery being utilized in any given building at any point in time. And this application actually was done in 2001 at the Mayo Clinic in Rochester, Minnesota. So it's actually been out there for quite some time, 20 years. What does it look like? This is a pretty simple example. You got your boiler on the bottom, air conditioning unit or chiller on the top, and you've got a heating load that the boiler creates. The way the heat recovery chiller works is that water's coming back at 120 degrees. You run it through the heat recovery chiller, produce 140 degree water. And these are just simple examples. The numbers might be different, but the idea is take the water coming back, warm it up, and substitute or help give the boiler an assist. Same thing on the cooling side. Your chiller's creating 45 degree water or whatever, goes out into the building, satisfies the load, comes back at some temperature, 55. Let's run it through the heat recovery chiller in a side stream fashion, and let's put 45 degree water or whatever the temperature you wish is back into the system so that you're actually assisting on the cooling side as well. So assist on the heating side, assist on the cooling side, and that's really the concept of a heat recovery type of chiller. A little bit more complicated example, only intended to say this is what a system might look like in a fuller form: expansion tanks, heat recovery pumps. To the extent that you can satisfy the entire load, you might not even have to run your chiller or your boiler, depending on how well-sized your heat recovery chiller might be for a particular application. Not just a single location, but take a central plant, perhaps a university or a city, a small city that has multiple load locations. You don't have to do heat recovery on every portion of that central plant. You might just put it in one particular spot. As you see in this example, the boxed in area is a place where we're saying, hey, we might have some application out in the central plant. Could be a dormitory, could be a gymnasium, could be a kitchen, or any type of application where you have both a heating and a cooling load. And at that point, you'd simply just replace that one portion with a heat recovery chiller. And that's the example you see here. We just put the heat recovery chiller in, and we're actually assisting with the load along the way. And actually also helps reduce carbon dioxide as well by introducing a more efficient piece of equipment. Everybody always wants to see an example, so I'm going to accommodate that just to put some meat on the bones of this type of application. Natural gas boiler, about 0.7 COP. A condensing boiler, just under 1. Electric boiler, 1 COP. But a heat recovery chiller is going to have a COP of at least 4.0 and higher. So the example here is designed to look at, all right, let's put some money to this. Let's say that our plant has an air-cooled chiller, 1 kW per ton, 11 cents per kilowatt hour, and know that dollar amount varies. California would be higher. Colorado, Utah, Wyoming might be lower, but the idea is it's still going to show some savings. So $6.60 to run a 60-ton machine for 1 hour. The boiler heat side, $10.31. We chose 1 million BTU and 60 tons as our example here. And when you put those two together, it costs you $16.91 an hour to run that particular scenario. Let's introduce a water-cooled machine instead. Put a water-cooled machine, 7 kW per ton, same 11 cents. That's a cheaper machine to run, a water-cooled machine, $4.62. Heating side, still the same, $14.93 to run that machine. If you're fortunate enough to have air side economizers as an option, you can use some of the outside air. You don't even have to run your cooling in some places, in some cases, but you still have the same heat load. So $10.31. If you're able to introduce a heat recovery chiller into the application, it's a little bit more expensive to run, but you're also getting free heat. So $7.05 for your chiller, free heating for the most part, $7.05. If you put them all together and you compare them, obviously scenario 1 with an air-cooled chiller was the most expensive. Heat recovery, $7.05. But even scenario 3, where you're not running the mechanical portion, still a 30% savings that you could achieve by putting a heat recovery chiller into a particular application. So we've talked about, what opportunities there might be out there, and we've talked about electricity. So maybe your tower is undersized. It adds redundancy to the system. It gives you better plant efficiency. What if the utility costs aren't your biggest play though? Well, you still have the opportunity to perhaps downsize or use your cooling tower less. So you've got some water savings that you could share with your customer as a potential savings, as well as footprint. Remember at the outset, we talked about, the boiler's a certain size, the chiller's a certain size. But if you're able to introduce a heat recovery chiller in there and downsize both of those, the boiler and the chiller, you may actually have a smaller footprint and a lower first cost for your customer. So potential savings are not just related to electricity use along the way. How do you go about analyzing one of these types of opportunities? Well, the most important thing is to understand your loads. And you have to have a simultaneous heating and cooling load in order for this to even be considered. They don't have to be equal. And if they're not equal, then you have to have a source or a sink. But you have to understand the amount of heat that you could save, per se, in order for a heat recovery opportunity to actually go ahead and work for you. But we can help you with that analysis, but as an engineer, you kind of have to know what your loads would be in a particular location. What's driving all of this? Well, this whole idea of electrification is originally a buzzword, but now all of a sudden it's gaining a lot of traction throughout the country. And essentially, we're seeing many places take out other fuels that have traditionally been used for power and other applications, and they're saying everything is going to be powered by electricity instead. And so this type of application will serve that particular space very well. It's happening in lots of places. Berkeley, California was the first city that has banned natural gas. It's going to take them a while to get there, but New Jersey has done so. 8 states and DC and Puerto Rico have clean electricity goals. A couple places in Colorado, Denver and Boulder, my understanding is they've started to go down that path as well in terms of removing natural gas from the portfolio. And I always thought, well, what's wrong with natural gas? And I'm coming to learn that there is some problem with natural gas. Fairly clean burning fuel, but methane, which is a part of natural gas, is actually turning out to be a significant negative byproduct, I guess, of CO2 and burning CO2. And a lot of those leaks come from the oil and gas operations as well as infrastructure in cities. And that's why cities are so strongly pushing to get rid of natural gas. July 15th of this year, a report in the Geophysical Research Letters found that methane emissions were actually twice what the EPA had estimated in some cities. So pretty significant reason to move away from natural gas. So the last slide that I have to talk about is, so what does multi-stack offer? How can we go do this technology? The first one is what we call an MSR. It's a water-to-water heat pump that has a reversing valve in it. So it's either going to do heat or cooling, but that's one way we can capture heat. Another one is a dedicated heat recovery for simultaneous heating and cooling. So you can do both. The one above it is just you're either going to heat or you're going to cool. The MSH product line can do the both. We're really excited about the next one, which is a high lift turbo core heat recovery opportunity. Turbo core, Danfoss, the magnetic bearing oil-free compressor, they've come out with a new model that allows us to do higher lift, which allows us then to play in the heat recovery space. So we're excited about that offering. The ARP is an air-to-water heat pump. The very first one was a water-to-water. This is air-to-water, has a reversing valve. This is our either-or version. It either heats or it cools. And then the last one, ARA, very popular in the Pacific Northwest, and now starting to become more popular in the center part of the country, Colorado, Utah. It's an air-cooled heat recovery machine, so it can heat and cool simultaneously, and it can also have an integrated free cooling coil embedded in it as well. So those are the things that multi-stack brings to the table with respect to product lines. We think we've got all the applications covered here. So Andrew, that's my last slide. I'll turn it over to you and let you kind of perhaps deal with some questions.
Great, Pat. I think we're just going to pause on the questions. Thank you very much. I'd like to thank all of our guests for joining. If you do have some questions, please reach out to your Long sales engineer. We're happy to answer as many questions as we can regarding this topic. We're all very excited about it. Again, so thank you very much for joining us. Please join us next week. Sean Davenport Smith, another sales engineer here at Long, is going to be talking about the future of boiler draft systems. Thanks, everybody, and we'll see you next week. Bye.
Thank you all.